formation physics using the large-scale structure in the universe, especially the galaxy clustering and galaxy lensing of red and blue galaxies and so on. Okay. Apparently, there's a lot of technical details. There's 2 hefty papers I'm going to talk about. So if you want details, you can go to YouTube or AstroPH. This one has appeared yesterday on AstroPH. This one has published. So maybe there are better versions of me talking, but we'll see. Really, what is quenching? Quenching, the term quenching briefly refers to the relatively abrupt shutdown of star-forming activities in galaxies. And what causes quenching, the question of what causes quenching is really fundamental to our understanding of the galaxy formation physics. So I try to illustrate the abruptness here, but you get the idea. And yesterday, David was talking about, OK, apparently halo mass is akin, and we really want to try to find the second variable that help us in understanding the galaxy formation physics better. And also, this post is simultaneously showing up on Twitter. Unfortunately, the conversation immediately goes into the argument of which one is fancier and cooler, whether stars or galaxies. But my talk here really try to answer this question, OK, do we need a second variable as a level of observational systematics and statistical errors as of now, OK? And I tried to, this sort of a response to Andrew's. That's up to you. I like galaxies better. Oh, you had a response even in the bottom, right? OK, anyway. Yeah, galaxy includes stars, so we're like a superset of them. Oh, yes, that's right. So this is really a response to Andrew's slide in the morning. Standard HOD logic is really sort of different, at least in my mind. There's other HOD practitioners out there. I can control their mindset. But what I really want to do is I assume mass only, try to describe everything. And it seems like my model really can fit everything so far, at least in Sloan in the local universe. And what I really want to do later is really try to populate mocks, use my schemes, use my inferences, and try to find more observables to do a better and more comprehensive comparison to eventually find the second variable, and then go for more complicated models. There's another scheme that's like start with a maximum assembly bias and find everything such a mess and hard to fit and struggle to find another model that can fit all. I believe there's got to be some kind of sweet spot in between, right? Eventually, we're going to converge into a right model that also includes the right way of implementing, for example, assembly bias and finding the second variable. Last week, I was in a meeting that's populated by observers. Everybody starts a slide by showing this. How many people have seen this before? Raise your hand if you are familiar with Ponedor paper. OK, so this is one of the leading theories, at least in observers' mind, how galaxies are quenched, OK? Apparently, Ponedor 2010 going to Sloan and Cosmos, they're trying to find the distribution red galaxy fraction, okay, intensity here, a red galaxy fraction, as function of environment and stellar mass. They found that apparently the distribution seems to be rectangular here. These 2 twins are mathematically separable. So that's why this idea of environment quenching and stellar quenching is super popular. But however, there are several caveats. First of all, the environment defining observer's mind is really, really very, very different from theorists, OK? The distance to 5th nearest neighbor is very hard to quantify in theory and simulations. And also, Ponedor 2012 further find that environment quenching is not entirely due to satellites. So if you look into centrals alone, they're really, in their mind, it's quenched by stellar mass alone. And also, if you really want to find, OK, whether the stellar mass quenching is ultimately coming from halo, is very hard from observations because it's very hard to really find the true mass, underlying mass, halo mass of those systems. That naturally leads to another theory, which is called the halo mass quenching. There's an interesting experiment done by Gabor and Davey et al. 2015. They just go into hydrodynamic simulations, find where the hot gases are. Those hot gases are real shocked by the just gravitational collapse of halos. And they just populate the galaxies, they just find the gases that are embedded in those hot halo and make them red. And they can actually recover this trend observed by Ponedor. So it's the same diagram, environment, stellar mass, and those dash curves are from the Ponedor paper, and their distribution are a simple experiment showing that halo mass quenching alone can actually entirely explain everything observed in Ponedor 2010, OK? And we really want to distinguish these 2 scenarios. See, I'm showing it's a different diagram, but also showing the red galaxy fraction. But for centrals alone, that's why this kind of a sort of tightly correlated band. This is stellar mass. This is halo mass. And in the first scenario, that's advocated by Pronato 2010, you have the red galaxy fraction going only as a function of stellar mass. If you have a higher stellar mass, you're going to be more red, and it doesn't really care about the halo mass at fixed stellar mass, okay? But in another theory, the halo quenching theory, the trend is exactly orthogonal. So basically, it doesn't care about stellar mass, and it only care about how massive your main halo is. Of course, nature will do something like maybe something in between, but in our simple experiment, we really want to just distinguish which one really is the dominant factor in quenching at least the central galaxies. The way we're doing it is apparently the diagram shows the central galaxies, at least they're distributed in different halos if you try to tell the color split in terms of their halo occupation distributions. So the two scenarios definitely going to predict very different, not necessarily very different, but different color split in terms of galaxy clustering and galaxy lensing if you look at the red and blue galaxies and so on, okay? And we start from this IHOD model we developed, Rachel and I developed early in May. The I doesn't really mean anything, it just means something fancy. So anything fancy starts with an I and is lowercase, so IHOD. And the three important traits of this model. So first of all, the IHOD is a global description of halo occupation distribution on the 2D grid of stellar mass and halo mass, okay? It's not just a function of halo mass. And also it has a way of accounting for incompleteness in stellar mass samples in a consistent way. And the most important part is that, okay, yeah. It can take into account like almost 80% or more galaxies than the traditional HOD methods can get. So basically we can include those parts on this stellar mass versus redshift diagram, and also this part. I heard something. Okay, go. Oh, sorry, this is for the overall galaxy population. P just the probability distribution of galaxies at fixed halo mass. Yes, sorry, yeah. Hasn't gone to quenching yet. So, but this is a starting point. In paper 1, we try to describe overall galaxy population using this model, okay? Because of the humongously more galaxies we can include, the system, the signals we measure really good. We can get a very good constraint on the IHOD of overall galaxies. And then we just developed two quenching models. The first one is a halo quenching model. You've seen this before. So basically, we try to divide, for example, for this spin from 9.6-ish to 10, we divide the sample into very thin redshift slices. I construct like single HOD within those thin slices and weighted them afterwards to get the overall signal. Okay, so we are not going to throw away those galaxies. They're very important because they actually see they're mostly red. There are a lot of galaxies there. Okay, and this is going back, the first quenching model we have. So for both the central and satellite galaxies, this is a stellar mass, this is a halo mass. The color indicates the red galaxy fraction, and in this case, the red fraction is tied directly to halo mass in both cases, although we allow them to have different functional form, functional different dependencies on halo mass, okay? But still, the overall quenching direction is horizontal here. And another model is we call this hybrid model. So basically, you've seen this before. This is central galaxies. Quenching is really dominated by stellar mass. But for satellite galaxies, inspired by Pronato 2012, we allow them to have an extra dependence on halo mass, which is a natural thing to do. That's why the quenching error is sort of like 45 degrees here. So the idea is like we can use these two quenching models and try to split the galaxies into red and blue based on the overall IHD we got, okay, in paper 1. And that's the scheme we have. A good thing about this is like we can do it via 2 steps. Because we're doing splitting within the best fit model, whatever you can get out of the quenching models, it can automatically recover the signal of the overall galaxies. And also, we have very much fewer parameters than traditional HOD models. They have to just treat different red and blue samples independently. And I've talked about this before. Also, the more galaxies we get, like 80% or more galaxies we get, really help us tremendously. Now we directly go to the best fit of clustering. Top row, lensing. Bottom row, left is for red, right is for blue. The data, the circle and squares with error bars are measurements from Sloan. And the dash curves are from the hybrid quenching model, which relies on stellar mass to do the quenching for central galaxies. And solid lines are a best fit from the halo quenching model. Overall impression is like they look really, really very similar. So if you look at red galaxies, they don't really produce any kind of distinctable differences in terms of best fitting. But if you really zoom in on the massive blue galaxies here, I help you to zoom in here. And remember the y-axis here is like 10 orders of magnitude. So if you look at the differences between dash curve and solid curve, they're actually pretty big. And we just zoom in further on the blue galaxies with stellar mass higher than 10 to 11 solar mass. And again, those are the measurements. This is the hybrid model, halo model. The curve, the thick curve are just the best fit predictions from each model. If you just do a simple virial chi-square, because here is only 2 orders of magnitude dynamic range here, apparently this one gives a much better fit than this one, okay? So really the key discriminator of two models are the lensing signals of the massive blue galaxies. And that directly translated to,
can you go one slide back? In the clustering for red galaxies in the lowest.
yeah, this part, this part is just ridiculously hard to fit because the volume is so small. Your estimate bootstrap, the error is always underestimated. And the volume is dominated by basically coma. So it's notoriously hard to fit for any kind of models. One is matching, HOD, SLF. Nobody can fit that part.
So you just throw it away because by eye,
But yeah, you won't change. They don't contribute any kind of differences in chi-square between the two models. So that's a comforting part. We don't really rely on them to provide the.
The only difference is the quenching with satellites, right? Quenching of centrals and both models here is the same, right?
No, quenching centrals. The hybrid model is like the red galaxy fraction only depends on stellar mass. And the halo quenching model only depends on halo mass. Because they're scattered between these two, they're very different, actually, if you go to massive part of the galaxy population. That make sense? That's why we see that the quenching arrows are orthogonal on the diagram of F-red. Right? That's the difference. No, that's for centrals. Yeah, that's for centrals, yeah. The centrals really provide the most leverage. Yes, yes. Say it again, sorry.
The model's the same for that bin and clustering.
This is actually not quite different. There's still like maybe a factor of 2, not maybe lower than that difference in terms of their best fit to clustering. But the most difference is coming from their fits to lensing. Because for clustering, you can get a different satellite population, make the one halo term better fit. But for lensing, really, the underlying mass of the host halo of the centrals, they're the dominant factor without those contamination from satellites. So if you just compare the overall chi-square, so halo quenching is a better model. That's it. Mainly driven by the difference caused by the lensing, the fit to the lensing profile of massive blue galaxies.
So this is where it all comes.
Yes, pretty much where most of the problem comes from. Yeah. We don't really have a lot of constraint on lower mass systems. Yes, that's right.
But physically, this makes sense, right? If you just like a rectangle kind of thing, then it is really about 10 to the 30th sort of mass.
Yeah, absolutely. I'll come to that. Yes,
we have some model to show it.
Yeah.
You have a strong transition at 10 to the 30th sort of mass, beyond which you have a lot of
Yeah. Absolutely. Yes. Yeah. And as I mentioned, this directly implies that the average host halo mass red and blue centrals at fixed stellar mass, they should be very different, okay? And here is directly showing that. Here I'm showing the average host halo mass as a function of the central galaxy stellar mass split into blue and red. The circles are measurements from Mandelbaum et al. It's also showing up yesterday using those locally brightest galaxies. They're purely a central galaxy sample. It's a very high purity, and also they're not biased against colors. So that's why we can't really go to max BCG or red mapper. And if you measure their weak lensing masses, they're showing up here. And the halo quenching model provides prediction that's shown by the thick solid curves. They grew very well. And the dash curve showing the prediction from the hybrid model, it just like failed to describe the strong bimodality between these two in terms of host halo masses, okay? And this is really like the key observable in separating these two quenching scenarios. And of course, you can talk about assembly bias if we provide maximum assembly bias in terms of the age matching model. You can also produce qualitatively description of the lensing and clustering signals. But if you plot them against, in this format, like average host halo mass as a function of galaxy stellar mass, the thick curves are, again, the prediction from the best fit halo quenching model. The dash curves are from a separate traditional HOD method. And the cyan and magenta are coming from the age matching model. They, first of all, they overpredict the amplitude for the blue galaxies. And also, they predict that the blue galaxies, blue centrals, ought to occupy in more massive halos than the red central galaxies, at least in this part of the stellar mass function. Oh, sorry, stellar mass distribution. Okay, this part reverses sign, but because they choose a different indicator for quenching in age matching marks. Okay, and that pretty much said that okay, these are observable, which is directly accessible from weak lensing measurements. Really, the key discriminator in discriminating, okay, which one is doing most of the heavy work in doing quenching central galaxies in the local universe. Okay, and one more slide just showing like why age match model sort of failed in this comparison. This is showing, again, this is stellar mass, halo mass, red galaxy fraction. At fixed stellar mass, the age matching model tend to place blue galaxies into younger halos. And from Cristiano's talk yesterday, we know the younger halos are pretty much more massive. And so that's why they're showing up here. That's why at fixed stellar mass, the blue galaxies, blue centrals, actually occupy more massive halos. That's directly ruled out by the observations of LBGs. Okay, so here the directly go to conclusion. And first of all, so far we don't find significant evidence that we need a second variable yet. Although Miyataki and the circles observation may provide some evidence that okay, the gap is there. Maybe we should try to fix that by adding a second variable, especially on the massive part of the stellar mass function. Okay, and though this is directly related to Ho Jun's point that the critical masses for the quenching of both centrals and galaxies we infer from the best quenching model, halo quenching model, is about 1.5 times 10 to 12 solar mass. That's pretty much in perfect agreement with the canonical halo quenching model, because above this mass limit, the halos are massive enough so that you can do a lot of real shock heating of the infalling gas, and that's inhibiting a galaxy formation, quench galaxies, okay? And then this part is like apparently from the average host halo mass versus stellar mass plot, we know that quenching seems like it has to be done primarily via halo quenching model, rather than you just boost it up assembly bias trying to separate them into ages and the halo masses. So that's it. Thanks.